Enhanced oil recovery technology in Daqing oil field. Part 1. Introduction of enhanced oil recovery technology at Daqing oil field. Part 2. Introduction of Daqing Exploration and Development Research Institute. Basic information of Daqing oil field. The main part of Daqing oil field is Heilongjiang province, located at the north of Sengliao Basin and west of Sengnan Plain. Daqing oil field is the largest oil field in China. There are 7 local structures in main part of Daqing oil field. Lamadian, Satu, 幸福港、太平屯、高台寺、葡萄花、奥波塔、multi-layer sandstone reservoir, including 3 formations, 41 bed cells, and 136 sublayers. Vertical lithophase section of Sartu reservoir in Daqing oil field. Reservoir parameters: depth around 660 meters to 1,842 meters. GOR 21 to 75 cubic meters per ton. Permeability 0.1 to 2 deci. Crude oil density ranges from 29 to 37 API. Porosity 17% to 27%. Freezing point 23.2 to 38 degrees. Oil saturation 53% to 72%. Wax contact 21 to 28.7%. Temperature at the reservoir 42 to 73 degrees. Sulfur 0.03% to 0.2%. Reservoir original pressure 4.2 to 17 MP. Salinity 5,819 to 10,100 ppm. Bubble point pressure 4 to 11.8. Viscosity 2.5 to 10.4. By the end of 2009, Prude developed 38.8 billion barrels. Recoverable reserves 17.9 billion barrels. Recovery factor 46.2%. Cumulative production 14.9 billion barrels. Total wells, oil producer and water injector, 82,975 wells. Annual production, 293.2 million barrels. World cut, 91.4%. Junshu Oilfield Company Limited, a wholly owned subsidiary of CNPC, can provide all kinds of service of petroleum exploration and production. Development history. Phase 1 water injection at early time. Blind water injection. The water cut start from 0, 8%, 17%, 35% by the end of 1970s. Oil production. The challenge is that in active edge or bottom water and weak natural energy, the strategy applied is to maintain reservoir pressure at initial level. Technology used: pattern flooding. Result: stable pressure in reservoirs and sufficient support energy. Phase 2 water flooding and reservoir management by zone. The water cut increased from 30% to 60% by the end of 1970s. Challenge: low pressure and commingled water injection, serious single layer water breakthrough, and serious interlayer and aerial interferences, resulted in quick water cut rising and oil production decreasing in producers. Strategy applied: maintaining high and stable oil production for a long term and increasing water flooding recovery. Technology used: reservoir management by zone, water shutoff and fracturing based on water injection by zone. Result: water cut rising was controlled. Oil production was 1 million barrels per day in 1980. Recovery factor was increased by more than 10% in medium to high permeability reservoirs. Phase 3 reservoir management by zone, subdividing. The water cut increased from 60% to 80% in the 1990s. The challenge is that production declined in main pay zones, and the influence of high permeable pay zones with high water cut, mid-low permeability zones are poorly developed. The strategy is improve the production from middle lower permeability zones to to extend the production plateau. Technology used: physics description of subdivisions, logging interpretation of water flooded zone, and enhanced production of low production zone. Result: the production was maintained stable at 1.03 million barrels per day in the 1980s. Recovery factor was increased by 10%. Phase 4: development and adjustment by infill well pattern. During this phase, the water cut kept stable, as well as the oil production. In this phase, the challenge is that when primary well pattern enter the later stage of high water cut, fluid rate will increase rapidly, and further oil production sustaining was limited by no significant addition of new reserves. Strategy: enhance the production from the existing oil fields to sustain the oil rate and control the water cut. Technology: identification and evaluation of potential of the unbooked reserves. Monitoring technology of producing performance of poor and thin layers. Well pattern infill technologies. Comprehensive reservoir management technology, including zonation, well pattern, perfecting, etc. Result: production added from the unbooked reserves. Oil rate sustained at 1 million barrels per day in 1995, and water cut only increased by less than 1% during 1991 to 1995. The recovery factor increased by 6%. Phase 5: EUR development. From 1995 to currently, the current challenge is that major reservoirs enter the ultra-high water cut state. Water flooding recovery degree was only 40%, and the producing level from thin and poor layer and layers with unbooked reservoirs need further improvement. Strategy: expanded EUR developed and associated with water cut controlling and reserves potential trapping. Technology: description of heterogeneity in fluvial reservoirs, polymer flooding, water shutoff, and profile control in non-effective water injection area and reservoirs. Result: the production rate from EUR was kept at 200,000 barrels per day for 5 years. Recovery of mid-high permeable reservoirs increased by more than 10%. Ultimate reservoir recovery will reach 55%. Dajin has established a set of water injection development technology, which is suitable to the heterogeneity, multiple layer sandstone oil fields right now and make a lot of achievement. Development technology. Reservoir character, the workflow as correlation by deposition cycle. Foundation of full-scale field development. Zonal sedimentary physics. Foundation of first in field development. Unbooked reserves evaluation. Foundation of second in field development. Reservoir description. Foundation of optimization of reservoir management and EOR. Intra-heterogeneity evaluation. Foundation of water control and remaining oil development in thick zone. Vertical subdivision of deposition units. The minimum net P of single sand body, 0.2 meter, can be identified, even with poor continuity of interbanded shear marker, and the current resolution of wireline logging is 0.2 meter. Physics map. Before subdivision, all sand bodies in different wells seem to be in good continuity and well pattern perfect. After subdivision, realized that the previous well pattern was incomplete. Later on, subdivision of microphysics. Based on coring and wireline logging data, the minimum area deposit unit and the individual sand body can be identified. (3D deposition modeling) on the basis of reservoir character and area physics analysis. An advanced 3D reservoir properties modeling workflow is developed. Then quantitative 3D description is realized. Intrastructural heterogeneity description method of rural thick beds using the single channel sand body, single pot bar sand body, interlayer description technology. Controlling non-effective, effective, and lower effective water injection. Short of high permeability part in channel sandstone. After plugging, liquid decreased by 100 barrels per day. Oil increased by 20 barrels per day. Water cut went down by 6.3%. remaining oil research, integrated study of sealed coin data, petrophysical re-evaluation for thin, pure sands, and water-flooded pay sands, reservoir monitoring, million-node numerical simulation, integrated analysis by combining dynamic and static data, artificial neural network identification. Over the past 40 years, indulging a series of technology, including evaluating initial saturation, identifying water-flooded zone, and cracking core data by decompression and desaturation, are developed. More than 150 sealed coring wells had been drilled, providing effective technology approaches for accurate remaining oil study. Well logging interpretation of water-flooded pay zone, comparison of log interpretation and sealed coin data, permeability exceed 200 millidarcy, accuracy more than 80%. Permeability ranges from 50 to 200 millidarcy, thin sands, around 80% accurate. Permeability less than 50 millidarcy, around 75% accuracy. It provides the basis for selecting perforation zone in infill wells and workover in existing wells with high water cut. Reservoir monitoring technology includes injection profile logging, production profile logging, separate zone sampling in producers, and chromatographic fingerprint examining, CO and casing resistivity logging, interwell microseismic logging, and pressure testing. Simulation technology, quantitative and refined remaining oil description needs, multidisciplinary correlation, and digitalized reservoir researches. This includes integrated work platform, United Technology standards, common shared database, integration of software package, keep compatibility, and unification of workflow, data flow, and software flow. By technology brainstorm, Dajing has developed matured and advanced technology software, accomplished integration of applied softwares, and established the workflow platform of multidisciplinary coordination. Lateral remaining oil description, refined to sedimentary microfacies. Polymer flooding. Mechanical of polymer flooding. Partially hydrolyzed were used in Daqing. The polymer has high viscosity. Polymer solution exhibit non-Newton behavior. Mechanical of polymer flooding. First, increase sweep efficiency. Adding polymer can increase the aqueous phase viscosity, absorption retention, decrease aqueous phase permeability, increase displacement efficiency, elasticity, reduce remaining oil saturation. It can also increase sweep efficiency. In this checking well, 27, 26, watered after profile. This is the displacement efficiency. You can see. Recently, some research results suggested polymer flooding not only expands sweep efficiency, but also increases displacement efficiency. Residual oil saturation is reduced by polymer flooding. This is the residual oil saturation after water flooding. This is the residual oil after polymer flooding. History for polymer flooding in Daqing. Laboratory test in 1965, pilot test in 1972, commercial pilot test 1991, industrial application from 1995. Small-scale pilot test performed in 1972. After 12 days of polymer injection, the producer got a response. Total increased oil was more than 600 tons. Incremental oil recovery was around 5%, using the well spacing 75 meters. West Central SAR-2 pilot test performed in the 1990s. Double layer zone, single layer zone. The single layer region, area 0.09 square kilometers, well pattern 5 spot, well spacing 106 meters, injector 4, producer 9. Two-layer region, area 0.09 square kilometers, well pattern 5 spot, well spacing 106 meters, 4 injectors, 9 producers. Polymer flooding performance. The water cut and recovery of central wells in a single layer region. This is the wort cut. This is the oil of the polymer. Incremental recovery 14%. Incremental oil production by per ton of polymer 177 tons. This is the central well results. Totally incremental oil recovery factor 14% and nearly 11.6%. The maximum water cut drop 25% and 21% low. Large-scale pilot test in the BE2 performed in 1991. Area 3.13 square kilometers, well panel, 5 sport. Well spacing 250 meters. Injector wells 25. Production wells 36. This is the performance for commercial pilot test in the BE2. Incremental recovery 12.5%. Incremental oil production by per ton of polymer 120 tons. This is the commercial pilot test in Lannan performed in 1994. Area 1.45 square kilometer, 5 sport, well spacing 212 meters, injector 16, producer 25, observation well 1. In the region 2 square kilometers, well spacing 300 meters, 9 polymer injector, 26 producer. We can see the wort cut decreased by nearly 25%. The oil increased incremental 12%. Incremental oil production per ton of polymer 120 tons. Performance for commercial pilot test in Lannan. Polymer injected. The maximum water cut drop 25% and 18%. Incremental oil per ton of polymer 126 and 91. Incremental oil recovery factor 14%, 10%. Application of polymer flooding. Daqing oil field has entered industrial scale polymer flooding application since 1995. Wort cut curves for central production producers in polymer flooding area. The drop down of the polymer and then increase again. This is the annual injection amount of polymer in Daqing. More than 160,000 tons. This is annual oil production by polymer flooding in Daqing oil field. More than 10,000 tons per year. Polymer flooding plays a very important role in the Daqing oil field. From 2003, the annual oil production by polymer was more than 25% of the total production. In 2018, more than 30% of the total. Technology of polymer flooding. Some technologies were applied or developed to improve polymer flooding results, including reservoir engineering, production engineering, surface engineering, dynamic monitoring engineering. Polymer quality evaluation. This is the technical specification of polymer. Scenario design. A set of scenarios optimization technology has developed. Result of programmed design optimization includes analysis geology, description of reservoir, layers, combination, and well pattern. Injection model optimization, injection parameter optimization. Polymer selection. Polymer properties analysis. B. Rheology behavior. Solution stability. Reservoir character. Water components. Compatibility with reservoir. Increase oil recovery. Polymer flooding control degree. Numerical simulation. In comparison with commercial simulation, the notable factors are as following. Polymer elasticity process, multi-polymer commixing flooding process. Adjustment technology. The polymer flooding process can be divided into 5 periods. Based on the PV injected, 0 to 0.5, watt cut increase in PV injected from 0.5 to 0.15. The watt cut start decrease. Improving polymer flooding result. For problem existed in different phases during polymer flooding, carry out tracking and adjustment to ensure polymer flooding effects. So no effective phase using the large interlayer permeability difference, using the deeper profile control of a stratified injection, high molecular polymer per log. Word cut dropping phase. Polymer flooding effects lag. Injection pressure increase. Difficult to show production and difficulty injection. Measures adjusting injection production parameters for removal of production valve fracture and injection valve plug. Word cut re-increasing phase. Difficult production, high injection pressure, and failure to complete injection, high permeability and high word cut. Adjusting injection production parameters for injection production valve fracture and booking higher permeability layer. Follow up water flooding phase. Ultra high word cut increase and great word cut difference. Measures changed over to water flooding in phases to adjust the injection quality of valve group and inject water periodically to ultra high word cut. Stratified injection pressure adjustment. Polymer flooding effect after separating injection. Proportion of water absorption thickness. Surface engineering. Polymer injection allocation technology. Produced liquid dehydration technology. Produced savage water reinjection technology. Chemical treatment agent server. This is the electric dehydrator polymer dispersion unit. Dynamic reservoir behavior monitoring technology. Non-collective flow type electromagnetic flow monitor. Tracing associated injection profile monitor. Pulse neutron oxygen activation monitor. Collective flow type electromagnetic flow combination. Different produced liquid profile continuous monitoring. Conductance associated flow produced liquid profile monitor. ASP flooding. Mechanical of ASP flooding. Relation of the interfacial tension, capillary numbers, displacement efficiency, and remaining oil separation. Ultra low IFT interface tension can get higher capillary number and reduce residual oil separation. Micro displacement result. Residual oil after water flooding, the value. Residual oil after polymer flooding, less oil. Residual oil after ASP flooding. history of ASP. Laboratory test in 1987, pilot test in 1994, commercial pilot test 2000, industrial application 2007. Pilot field test. Since 1994, 5 pilot field tests were carried out. All of them could achieve about 20% original oil in place incremental over that for water displacement. 3 injector for producer EUR 23%. 6 injector 12 producer 22% increase. 4 injector 9 producer 21% increase. 4 injector 9 producer 19% increase. 1 injector for producer 25% increase. Pilot test area. Commercial field test. From 2000, 3 large-scale ASP flooding commercial field tests were put in practice by utilizing self-development surfactant product, alkaline, ASP flooding commercial field test with location map. The first one 2 square kilometers, spacing 250 meters, 17 injectors, 27 producers. Test gained significant results of oil increase and water decrease, which are predicted to achieve 20% of the recovery factor. This is the technologies of ASP flooding, development and production of surfactant. Establishing analysis methods for ABS, raw and products. Establishing refining disposal technology of AB. Refining technology is formed based on the boiling points differences of various components in AB, which is optimize the performance of surfactant. Inventing unique sublimation technology for ABS surfactant. The neutralization and mix are separated in the traditional process, which is a complicated route and is difficult to measure accurately and be carried out in industry device. After a number of calculation and laboratory experiment, integration process of mix is invented, which realizes 2 steps operated simultaneously in one kettle. This is the optimization of ASP scenario design. Optimization of prescription using the chemical screen, performance evaluation, optimizing the injection model, includes core flooding, numerical simulation, design the injection program, injection model, slug and chemical. Form the injection scenario. through years of research. Comprehensive optimization of ASP flooding injection project had been formed, including chemical screening, performance evaluation, chemical dosage, and injection mode. The main problem for ASP flooding production engineering is serious scaling well, ceramic rotor, anti-scaling piston, scale prevention screw piston, and using the chemical injection and perforation. Based on the ASP system, the ground process is optimized, and the technology of targeted fluid injection and perforation is determined. Produced fluid processing. The special scale prevention agent, demulsifier, and produced fluid handling equipment were developed for ASP produced fluids. Treatment technology of produced water. For section of treatment, including a two-stage oil removal and a two-stage filtration, were developed and brought into practice. After treatment, the produced water could reach the standard of injection. At 2007, ASP flooding was stepped into industrial scale application in Dajing oil field. See heavy oil field CSS practice. Overview of the sea heavy oil field. Mirador reservoir, fractured conglomerate reservoir, rock fluid property, reservoir simulation, production behavior, CSF, field development plan, contractual. It is located in the Kagwan Putumayo Basin. Current royalty 6%. Code production from 2008. Thermal production from 2018. CSS pilot execution in 2018 to 2019. Extension 2021 to 2023 of forward massive thermal development. Background. Three structural compartments, north, south, and central. Segment central north and central north. Development and reserves focusing on central compartment. Field development mainly with horizontal and some deviated and vertical wells. 150-meter interval distance in P zone. Currently 45 oil wells, includes 33 horizontal and 12 vertical and deviated wells. 7 non-producers, either suspended or abandonment. 2 oil reservoirs, Mirador as the primary porosity and conglomerate secondary fracture porosity reservoir. Cumulative coal production 4.4 million barrels. 3.7 million barrels from Modulo and 0.68 from Conglomerate formation. Total Modulo original oil in place 439 million barrels. 60 million barrels in the north, 336 in the central, 43 in the south. Total sea formation original in place 150 million barrels. Focus currently development focus on in central development area, Modulo and sea reservoir. Original in place 486 million barrel. Ultimate reserve 29 million barrel using the cold method, and 47 million barrel with thermal methods. Please map seismic and wells. Seismic includes 184 square kilometers 3-dimension seismic and 237 kilometers of 2-dimension seismic lines. Wells 44 producers includes 31 horizontal and 13 deviated and vertical wells. One disposal are 55 as the water disposal. One suspended well K15 in evaluation and 7 abandonment. Regional section. This is the well 1093-8. Petroseismic processed in 2014 from Chipo to the sea field. Sea field structural compartment. 40 anti-line northeast to southwest oriented 28 kilometers. 3 target Modulo, sea, and basement. 3 big areas based on structural fractures, north, central, and south. Sea field deep pipeline pipe section 236. This is the section 130. Sea field cross time section from south, central north, and north. Fault system 3 scale fractures. Big scale force including 18 force, medium scale and small scale, which is in the well fracture. Big scale fault orientation system northeast to southwest main system and northwest southeast secondary system. Different scale that have this diverse impact on the reservoirs. Small scale affects sea formation. This is the fault mapping. Modulo depth structure map. Modulo formation is the main target in the heavy oil field. Average gross thickness of 120 feet. Even strong thickness variation is presented along the field. Towards north and south area, thickness is thinner than central area. Some area towards west, G9 is not present because of the either erosive event or no deposition due to structurally higher than other area. Based on information of existing thick fields, using lithology physics, logging physics, and seismic physics, proposed strategy derivation of Mirador formation is upper Mirador and lower Mirador. C formation. Uncomfortable below the Mirador is the secondary production target in the C heavy oil field. Based on information of existing C field wells using lithology physics, logging physics, and seismic physics, the proposed strata derivation for this section is upper C, middle C, and lower C. Cretaceous age is under evaluation. Composition of conglomerate that covers this area and is part of the sequence due to the presence of a half graben on the area, which allows sediment conglomerate in this part of the basin. C composed mainly of soft polymictic conglomerate makeup of quiz, notable presence of meteorographic and igneous rock. Basement structure. Basement producer potential is an evaluation. Mirador and C fractured overlies uncomfortably basement. Payara 1 E8 and Chile H8 and Durello A1 area. The basement has been described as metamorphic rock. In K15 well, basement has been described as a sapphire seed green color. C-field over stratigraphic column. C-field section basement, C formation Mirador, Alayan, reservoir formation, Mirador and C. Only Mirador and C formation has been tested as isolated basement with oil producers potential. Upper Mirador, lower Mirador. C formation. P73 into 3,440 to 3,540 samples. Poor to fair recovery of milling. This is the reservoir general description. Middle, the reservoir is the primary porosity. Thickness 120. Net oil thickness 80 to 80 ppd. The depth 3,200 ppd feet. Oil viscosity 3,341 at 138 degrees. Porosity ranges from 30 to 33%. Permeability, the air permeability at 1,200 psi ranges from 3,300 to 7 deci. From a conventional core study, effective permeability 3,345 millideci from a core advanced rock study. Original oil pressure 1,362 psi. High decline of original pressure in drainage area. Current reservoir pressure around 420 psi and 1,200 psi. In the CSS pilot area, with pressure between 693 psi and 814 psi. Recovery factor around 7%. Oil-water contact in the west changes towards the west is 2,159 feet. In the west, 2,040 feet. In the east, lowest known oil, 2,142 feet. The east estimated oil-water contact, 2,200 feet SSTVD. The producing contact is different depending on the segment zone and the rock type. Characteristics: horizontal and vertical reservoir heterogeneity, high unfavorable mobility ratio, high water production and pressure decline, high initial production decline followed by the stabilization. Pressure map, conglomerate formation is the second porosity with the fracture reservoir. Thickness 160 feet. Net oil thickness 80 feet. Depth 3,100 to 3,300 feet. Oil viscosity at reservoir 3,341. Porosity ranges from 5% to 15%. Permeability 001 to 11 millideci in metric from a conventional core study. The effective permeability more than 5 deci associated with the fracture. Reservoir temperature 136 degrees. Original oil pressure 1,472 psi. The current reservoir pressure around 1,100 to 1,300 psi. Not much decline. Recovery factor 3.6%. Oil-water contact. The lowest known oil is at 2,256 feet SSTVD. Characteristics: high oil rate near area of more fractures. Fracture provides essential storage capacity and the permeability. Water cut is higher than Mirador and rises quickly. Constant high decline. Mirador Reservoir. Mirador sand group classification as subdivided as Upper Mirador A, Lower Mirador sand B, Lower Mirador sand C. In the A is around 16 feet, B 30 to 33 feet. Net oil in the Mirador C 14 to 20 feet. So together Mirador sand around 60 to 69 feet. Upper Mirador sedimentary. Mirador core and E-log data provides values of porosity between 29 to 37%. Permeability between 400 and 18 deci. Saturation 80%. And grain density values from 2.65 to 2.74. Reservoir properties from the core analysis. Sand B. Mirador core and E-log provides values porosity between 29 to 37%. Stratic Mirador segment north, central north, central south, and south. Grid area 9,271 acres. Grid incremental 150 meters times 150 meters. Segment 4. Fort 19 was born. Fourth was model. 3D cells. Horizontal 4. 3 zones. Mirador zone, division and layering. Upper Mirador, Lower Mirador. Porosity seismic volumes. Permeability using the correlation between porosity and permeability. To calculate the permeability. 3D properties distribution in the upper Mirador A tops. This is physics, porosity, permeability, NTG, OWC, STOIP. All properties have 3D distribution. This is the layer 84. Layer 102. Layer 113. Oil water contact. In the north, 2,025 feet. Central 2,159 feet from the well L11. In the south, 2,089 lowest known oil from A2. Well, west oil water contact L11. So here from the resistivity, we can see the oil water contact at 2,159 feet TVDSS. mirrored or volumetric from a static model. Stoop 336 million barrels totally. Fractured sea formation from E8 well, porosity between 6% to 12%, permeability less than 10 millidarcy range, metric property related with high compaction. This is the open fracture direction and deep. Two main origins of the well skills fracture: northeast to southwest and north-northwest to south-southeast, between 50 degrees to 60 degrees and 70 degrees to 80 degrees. Fracture direction is not constant. Open fracture intensity. Fracture direction is not constant. The most is considered while horizontal designing. Two main orientation of small-scale fracture: northeast, southwest, north-northeast, west, south-southeast. Two deep tendency. Fracture direction not consistent. Volume. The stoop in the sea formation 150 million barrels. So, central area, Mirador and the sea formation stoop, totally 486 million barrels. Central area. Rock fluid properties. Fluid property TVT data from Mirador and the sea formation. The bubble point pressure 500 to 546 339 psi. BO is around 1.04, 1.03. The viscosity at a bubble point is around 2268 to 2000. Viscosity virus temperature. From here we can see the viscosity is very sensitive to the temperature. If the temperature increases to 210, the viscosity can decrease to dramatically in all wells. Relative permeability. Fraction flow. There is high preference for water displacement and channeling, fingering. Yes. Initial pressure and temperatures. Most representative measurements correspond to PBU, initial build-up measurement. There is some dispersion on the measurement given by the low fluid mobility, high restoration times. For Mirador and considering the high permeability around F7, the values measured on that well are assumed as the initial condition. Initial pressure 1263 psi. For the sea formation, and by the high density of natural fracture, considering measurement on E8 are assumed as the initial one. So the sea formation initial pressure 1472 psi, temperature 136.8 degree. Static pressure during the closure period in the year 2015, a fluid level campaign has been implemented in order to acquire static pressure data for supporting development plans. So we can see the pressure is restored to nearly the original level. In the FLO platform, also increased, restored dramatically. PSRZ platform. Mirador formation. We can see slow pressure restoration typically from heavy oil reservoir has been observed in some areas. Reservoir pressure decline in a high structural position. Pressure is maintained in the wells close to oil-water contact. Reservoir simulation. Seafield Central North using the code forecast. Central South using the code forecast and CSS kits and analysis. Main characteristic. Average permeability for Darcy. Porosity 28%. Viscosity 2250 cp. It is proved different models of PVT and oil viscosity. Initially was used in oil viscosity around 2000 3200 cp, GR around 30 barrels per barrel. But during the history match stage, and in order to reach the match of the oil and the BHP per barrels, it was necessary to reduce the viscosity to 2250 cp and GR equals 40 barrels per barrel, maintaining the original permeability and porosity values. This final value of viscosity can permit to represent the history production in cold conditions, as well as reach the oil peak production during the CSS in F10 P88 without refining sites and with suitable simulation run times. According to the PVT result, exists uncertainty in gas-oil ratio and oil viscosity, and it is possible that exists variation between around 2500 to 4000 cp. PVT analysis. In order to achieve historical production at certain points with viscosities of 2000, 3200, and 4100 cp. The model generates a minimum BEP up to 26 psi, trying to achieve oil production. It is observed how in the well the historical production value are not reached in some scenario associated with the flow capacity. Therefore, the permeability, the net thickness, or the viscosity may not be being adequately. For this reason, it is decided to take the average viscosity value of 2200 cp without affecting the original property of the static model. For the best science using the rock type 1, for the worst science using the rock type 2. In 2018, two CSS in F10 and P89. This is the history match for these two CS as well. Adjust the aquifer to history match the pressure. Analysis of thermal effects. There is a possible connection between wells that enhanced this application of area steam injection strategy. However, in further years, it is necessary to take information and evaluate the use of possible DD for steam conformance. This is the using forecast using different cycles. Production behavior. This is the history. Production behavior bubble maps. Horizontal wells, 231 horizontal wells. And vertical wells, 20. ECHOPS technology. The main objective of this analysis is to evaluate and understand the performance of CHOPS technology and jet pump artificial lift system in the seafield wells from reservoir and production point of view. ECHOPS refers to cold heavy oil production with sand technology. CHOPS technology with jet pump were applied in the well P73, 74, F87. CSS with the jet pump artificial lift system were applied in the F10 field. ECHOPS wells are F87, P73, P74 and F10, F87, P73, and P74 are derivated located in the west flank of the structure, and F10 horizontal is located up deep in the west flank of the structure. All of them are located in higher oil sand similar oil pay thickness in all these wells, around 70 to 100 feet, or wells close to oil-water contact with high water. Each of wells with high BSW and TD into the C formation with high torque, high wellhead pressure, the high water, proportional to production zone. Well flow, where low structure with low BSW. Well design vertical, going deeper into oil water contact, and C formation tested water formation can be affecting the each of the results. Each of the wells are located in the higher permeability zone and high BSW. High water behavior are mainly related to high permeability area and prox to oil water contact as indicated in the correlation of both map trend. Each of will be BSW versus permeability. High BSW in the area close to oil water contact, high BSW in high permeability zone, high BSW in vertical and deviated close to oil water contact. Each of pilot wells are close to the water oil contact. Therefore, the response and the efficiency of the technology was influenced by high water production. It is necessary to continue probing the performance of artificial lift jet pump system with CSS and with the sand control system. CSS. Development Strategy CSS 2010 Loose content oil saturation reservoir thickness has been recommended extensively both internally and by consultant. In 2014, a study, the mineral reservoir quality is good and appears suitable for steam injection. 2014 PetroChina expert. Sea oil field will be good performance of thermal recovery and development. 2016 the EU Alliance Global Leaders enhanced oil recovery. After screening of mineral characteristics, it was concluded the best option for enhanced oil recovery is thermal recovery with the CSS. 2018-2019 CSS mineral pilot execution with positive results. Steam Stimulation is a mature concept to implement in the sea heavy oil field. The pilot in 2018 to 2019. Pilot steam injection project in Mirador Formation was designed to evaluate parameters and incremental oil in thermal conditions to optimize the implementation of the SS process as the principal operation scheme of the heavy oil field. CSS pilot in P89 with cumulative oil 34,000 barrels before starting first CSS, and F10 with the cumulative oil 259,000 barrels, higher duplicated well in the field. The cycle of the SS single well process contains 3 stages: steam injection, soak, and production. The cycle starts first days of injection and finish once initial production condition before injection is reached. First cycle of CSS pilot in P89 started steam injection in August 28, 2019. And in F10H started steam injection on November 1st, 2018. Results are considered for expansion and massive implementation. Injection, the lesson learned. F10 injection lesson learned, real cumulative steam only 79% of the total plan. In the soaking period issue and lesson learned, soaking in P89. Soaking time delayed 11 days more than planned due to the operational problem. Production lesson in the F10 production result masked due to pump failure condition during September. P89 injection phase on August 28, 2018 was started the cycle stimulation according with the designed parameters. In general terms, was a successful stimulation with a normal behavior. In the injection pressure reached the temperature, quality, and heat volumes designed for this stimulation. Totally inject 19 millibtu per hour. So totally steam inject quality 78% and 564 degrees at the wellhead, and the total heat injected 11,415 millibtu, more than 3,170 31,762 barrels water was injected. Soaking phase. After cumulative steam injection of 11,415 millibtu, the well was closed for 19 days, which is 12 days more than projected due to some operational problems. During soaking period, pressure falls was recorded in the well to understand the dissipation of the heat and the fluid in the formation. In case of a successful dissipation, tubing head pressure will come down and will become zero. We can see the wellhead temperature decreased from 580 to 100 in 6 hours. The wellhead pressure dropped 600 psi in 2 hours, dropped to 60 psi in 18 hours, dropped to 5 psi in 2 days. This is the performance. This is the oil increased. This is the production in cold production. So we can see the initial oil increased to 374 barrels per day. In the cold period, is less than 100. This is the oil production. Middle F10 injection phase. On November 1st, 2018, was installed the cycle steam stimulation according with the design parameter. In general terms, was a successful stimulation with a normal behavior in injection phase, reaching the temperature quality. However, due to the operational problem with the new wellhead injection, was necessary to stop it. The total heat injected to the well was 6,835 millibtu, 79% of the target. Steam quality nearly 80%. Wellhead temperature more than 609 degrees. Wellhead pressure nearly 2000 psi. The injection duration 14 days. Totally nearly 20,000 barrels water was injected. Soaking phase. After cumulative steam injection of 6,835 million BTU, the well was closed for 8 days, 1 day than projected. During the soaking period, due to the failure in the wellhead, was not possible to record pressure full hour by hour. and well to understand to the dissipation of the heat and fluid in the formation. However, some data was recorded respecting the fall of the pressure and temperature. In case of a successful dissipation, tubing head pressure will come down and will become zero. We can see the wellhead pressure dropped quickly from 1000 to 400 to zero, and the casing pressure also decreased quickly. This is the production period. The initial production after the CSS, it increased to 294 barrels per day. Before the CSS is around 115. This is the water produced. And BSW during the initial following months ranges around 20 to 30%. Conglomerate formation CSS 5 C5 C5 in the cold production period is only 25 barrels per day. After injection CSS, it increased more than 160, increased dramatically. Modulo CSS pilot in 2022 and 2023 in 3 wells. P88, F12, and F10. The lesson in the injection period, no more it went smoothly. Soaking issue lesson learned. P88. After 2 days, the pressure and temperature in tubing and casing decreased completely. Soaking time delayed during running beam pump was found a restriction into the tubing at 979 feet. F12. After 8 days, the pressure in tubing and casing decreased completely. Soaking time delayed due to problems during the jet pump installation, ECHOPS. F10, the second cycle of the CSS, soaking time extended due to delay to run artificial lift system related to service company issues. Production period. P88, production restricted due to the field closure, shut down due to motor failure, pump replacement, submergency instability, possible sand blocking. F12, production restricted due to the field closure in May and June jet pump optimization. Modulo CSS. So we can see these three wells. The total length. Total length oil sand opened with a square P89 nearly 1,600 feet, F10 750 feet, P88 1,260 feet, F12 the shortest 590 feet. In general terms, P88 was a successful stimulation with normal behavior in injection pressure, reaching the temperature, quality, and heat volume designed for this stimulation. So wellhead temperature more than 600 psi, higher than the design. Wellhead pressure 1,767 psi, less than the designed 2,000 psi. Steam injection rate nearly 19 millibtu per hour, similar to the design. Steam injection rate cumulative steam 13,055 million BTU, larger than the designed injection rate 1,125 barrels per day. Steam quality 76%, a little lower than the designed number 80%. Days injection 33 days, Model 1. Soaking phase. After 2 days, the pressure and temperature in tubing and casing decreases completely. Soaking time delayed during running beep pump was found a restriction into the tubing. During soaking period, pressure fall was recorded in the well to understand the dispersion of heat and fluid information. So the soaking time started from February 20. Soaking time 12 days, and start production from March 4th. Production phase. CSS incremental lower than planned, merely affected by the restricted CSS wells during May and June, and additional losses of temperature in the reservoir. Production result masked due to operational restriction caused by the road condition. Soaking time averages 16 days. Dispersion time average 4.3 days. During well parameter normalization and trying to restart, it was shut down due to motor failure, pump replacement, submergency instability to restrict this well. Submergency instability possible indicate sand blocking. Cumulative oil produced at September 20th, 30,749 barrels in 200 days. This is the CSS result. Actual steam injection period, soaking, producing. This is the planned oil plant. This is the actual incremental. F12 CSS result. F12 start on January 4th. Currently, steam injection with good quality, but high well head pressure and minimum well head leakage. Finish in April 1st. 3 p.m. with total of 10,390 million BTU. Wellhead pressure 2000 psi, a little higher than the P88. Steam quality 77%. Injection days 31 days. Soaking phase. Start soaking period in May 1st, 2022, 3 p.m. 8 p.m. After 8 days, the wellhead pressure fall until 22 psi. Soaking time delayed due to problems during the jet pump installation because of the ECHOPS. 18 days of soaking time due to some contractual issues that affect start oil production. Production phase. CSS incremental lower than plan affected due restricted CSS wells production during May and June, affected the losses of temperature in the reservoir. Production result masked due to operational restriction caused by road condition. Cumulative oil production at September estimated 15,665 barrels in 124 days. The target is 38,000 barrels in 1 year. F10 injection rate. F10 in general was a successful stimulation with a normal behavior. In injection pressure reaching the temperature, steam quality, and heat volume designed for the stimulation. Wellhead pressure 1450 psi, lower than the planned 2000 psi. Steam quality 77%, a little lower than the designed 8%. Injection rate 28 days. Soaking. Soaking phase start on July 13th at 23 p.m. After 12 hours, the pressure and temperature in tubing and casing decreased completely. Tubing head pressure come down and become zero, indicating successful heat dispersion into the reservoir. Soaking time extended due to delay to run artificial lift system related to service company issues. Soaking dissipation of the heat through the reservoir will be longer, total 18 days, than first cycle, total 8 days. The benefit is the volume of the steam of the second cycle is much higher than the first cycle in F10. Steam volume and oil sand is larger in F10 than F12. This is the comparison, the first cycle, second cycle. First cycle, soaking 80 days, this time 18 days. Started production on August 1st. After first month, real production 99 barrels. Mirador CSS result. External factors had been affecting the steam cycle in different phases of soaking and production. Soaking time average is 16 days in the last 3 CSS. Dissipation time average 4.3 days in 4 cycles. Real soaking time is 11.7 days, average higher than planned 7 days. Soaking phase in wells like F12, F10, real time are 18 and 19 days, higher than the planned 7 days, and higher than dissipation average time 4.3 days due to external factors affecting the operation. During the SS production phase, P88 and F12 are affected due to the restricted production during May and June, and in addition, losses of the temperature in the reservoir. Higher steam injection volume per feet, it doesn't mean better result. P89 with less steam volume injected 6.448 BTU per feet has the better result. 11.72 million BTU per feet is the average injection in the last 5 cycles. Lining. Longer oil length, steam tolerate longer soaking time. P89, P88. In F12, F10, the second cycle keys, which are shorter oil length, 18-19 days soaking time. Water behavior. Totally in P89, the first cycle injected 31,000 barrels. F10, 18,000. P88, 37,000. F12, 29,000. F10 second cycle, 32,000. So it will last around 2 months with high watt cut. Then the watt cut becomes stable. Mejorada CSS pilot in 2022-2023. We have also noticed some interference between wells. First, F10 submergency fluid rate increased during P88 CSS, which indicates reservoirs are well connected. Around 2,813 barrels incremental oil was directly related to P88 CSS from February to March 2022. This volume from F10 should be counted as the incremental of P88 CSS. P89 submergency fluid rate increases during F10 CSS. Which indicates reservoirs are well connected between these two wells. Around 514 barrels incremental oil was directly related to F10 CSS from July to September 2022. If this is a continuous trend lasts to January 2023, around 2,056 barrels incremental would be expected. This volume should be counted as the incremental of F10 CSS. Besides the beneficial in neighboring wells, we are now checking the timing between cycles. The CSS effective period in P89, P88 seems to be longer than 1 year, so there is a possibility to evaluate a longer CSS cycle for the past 5 cycles. The interference between wells, after submergency here, and the fluid rate here increase during P88 CSS injection. After the P88 CSS, F10 submergency decreases to normal, and the production also increased during this the F10 FP88 CSS, and then come down to normal. This indicates the reservoir between P88 and F10 are well connected. F10 fluid rate increased during P88. You can see the production increase around 2,813 barrels incremental was directly related to P88 from February to March 2022. P89 submergency increased during F10 steam injection. After the F10 CSS, P89 submergency decreased to normal level. Also, the production rate this indicates F10 P89 reservoir are well connected. P89 fluid rate indicated during F10 CSS around 514 barrels incremental oil was directly related to F10. Another 2,000 barrels incremental would be expected. CSS strategy for future. It is required to analyze the behavior of the cycle based on variables such as injection pressure, oil-steam ratio, PIR. It is recommended to start with a low rate and then increase. Cycle 2 to cycle 6, it is recommended to take information and verify the injection profile to selective injection and start with the area injection. Cycle 6 to cycle 12, it is required to start the combination of strategy together with the fluid injection to increase efficiency and steam conformance, foam, gas, or steam flooding feasible. Steam efficiency and strategy. Start sequencing to new strategy. Select model simulation, analog fields, and practice. CSS strategy for future. To make pilots to change steaming strategy in order to improve steam efficiency. This proposal intends to improve the well response of the steam injection, increasing the reservoir pressure and simultaneously by past zone, production performance, and oil steam ratio can be increased. It is require validation by simulation and create a pilot in a group of wells. The main advantage is that this proposal does not require additional budget, only adequate planning between reservoir and operations. Injection, close production. Soaking, injection, close production. So in this way, all the reservoirs could be heated and improve the efficiency. Design proposal for the next CSS. This is the oil history match, water history match. Refined well, 50 times 50 feet. Parameters optimization second cycle in F10. Steam rate 1,400 barrels per day injection. Injection period 5 to 30 days. Steam volume 7,035 barrels to 42,000 barrels. 26,100 to 15,006 million BTU. Objective function oil cumulative second cycle. Summary result F10 second cycle. In order to find a balance between the oil cumulative efficiency of the oil steam ratio, water cumulative production PIR, it suggests the next around 17 days injection next time. Higher steam volume cause higher water production and less efficiency, but with high oil cumulative production. Low steam volume cause low water production and higher efficiency of oil steam ratio, but less oil cumulative incremental. Steaming strategy. With respect to the previous cycle, it was decided to increase the injection volume in the second cycle by around 30%. This is according to simulation result, and in order to increase the stimulation radius and achieve better results. On the other hand, according to the RG Gallen SPE 25794 steaming and operating strategy at midlife CSS operation. In order to improve the steam response, it is necessary to develop a strategy from the beginning of the cycle, which consists in increasing the radius height according to the volume and the pressure, and in this way manage to contact a new area and increase pressure. Field development plan. In the central area, using thermal cold production plus CSS expansion, recovery factor can be reached 7%. CSS extension increased recovery factor to 10% to 15%. Evaluation test and plans of enhanced oil recovery technologies to increase recovery, including chemical, thermal, and mechanical methods. So CSS wells, totally 106 wells in the long-term plan, 96 horizontal plus 10 deviated wells. Cycles by well, 4 to 12 for each well. Generators, 9 in the long term. Total cycle, 758. Steam injection pressure, 2010 psi at max, according to the current reservoir fracture pressure. Steam injection rate, average 550 million BTU per day. Steam injection rate per well, ranging between 1,450 barrels to 1,570 barrels per day. Estimated downhole steam quality more than 70%, assuming tubing isolation. Injection time for each well, 20 days. Generator maintenance, 10 days after each injection per well. Soaking time, 7 days in the horizontal wells, 3 days in the vertical or deviated wells. Only one CSS completion and pump. We can estimate the production can exceed 16,000 barrels. This is the drilling plan. And a production forecast. This is the CSS only forecast. Pilot steam injection project in Mirador Formation was approved to evaluate parameters and incremental oil in thermal condition to optimize the implement of CSS process as a pre-sample operation scheme. In August 2018 was initiated a pilot. F10 were selected and the following premises. First, production less than 150 barrels per day, BSW less than 15%, be in the platform F and P. After 1 year of production, it was possible to show that for both cases, the cycle injection of steam showed the expected result. In the case of P89, it was estimated that after a steam cycle, 82,000 barrels could be recovered. However, the result was 94,000 barrels was accumulated, more than 15% more. Considering the result obtained by FP89 and F10 for the term 2022, it was decided to extend the implementation of CSS in P88, F12, and F10. In order to make a preliminary evaluation of the result of the injected wells in 2022, a reversion with this production history was carried out. Wolf's obstruction in the mechanical pump wave pump switched to PTP, so fluid used to control the well has a thermal impact during the SS cycle, but still some damaged removed, and the well returns to a new higher code base. Previous 130 barrels increased to more than 600 barrels per day. Jet pump artificial lift system create a cooling effect due to motive fluid, so the production decline sleeper is stronger. Yeah, F10. This is the selective criteria. Net P 50. Total length more than 600 to 1,600 feet. Permeability ranges from 3 deci to 5 deci. Porosity are similar. So the parameter planned and real, as shown in this table. In general term, there are no significant variation in the injection volumes, and it can be concluded that the plan was fulfilled. In relation to the injection time, the variations are minor, and it can be concluded that at least 30 days were required on average. However, regarding the soaking time, this parameter was the one that presented the highest rate of the deviation. In P88, the well was soaked for 5 more days than planned. In F12, 11 more days, and in F10, 12 more days. The main reason for this deviation is due to circumstances of the force majeure, such as the closure of the road due to damage caused by the strong winter. Social issues and delays in the preparation. P88, 1,206 feet. The injection volume was greater than planned. Considering that the variation was very low, 92 million BTU, or less than 1% increase compared to plan, it is not considered that it has a great impact on the result. 25 days of injection was considered, whereas a real 33 days. Considering that the variation was very low, it is not considered that it has a greater impact on the result. Regarding soaking, of 7 planned, 12 were finalized, which is estimated to have a negative effect on the result, but not too much since the initial incremental seems as good as planned after soaking. F12, 590 feet. The injected volume went according to plan. 25 days of injection were considered, whereas a real 30 days. This variation has some impact on the result. The volume of steam per foot is open for discussion for further CSS. F12 oil length is only 590 feet. The steam injected was higher as 17.6 million BTU per feet compared to previous cycle in P89, F10 first cycle, P88. This is quite high. If the steam injected is kept at less than 10 million BTU per feet, the injection period could be shortened as 17 days. Regarding soaking of 7 days plan, actually 18 days was finalized, which is estimated to have negatively affected the result, since the real production were much less than planned, which was believed to be related to a cooled reservoir temperature. F10, 750 feet. The injected volume went according to plan. 27 days of injection was considered, whereas a real 28 days. The volume of the steam per foot is open for discussion for further CSS. Regarding soaking of 7 days plan, actual 19 were finalized, which is estimated to have a negative effect on the result, since the production is less than the first cycle in 2018, although much more steam were injected in the second cycle. It was believed to be related to cool reservoir temperature caused by the prolonged soaking time. P88 General Comments. The cumulative in 1 year incremental is 45,000 barrels, is tied to the green line. Parameters. The injected volume was greater. However, the variation has little impact. Artificial lift system. Beam pump has been used as artificial lift system, the same as suggested in the initial plan. Cumulative production. An important fact to consider is that this well was an restricted production parameter due to the closure of the field. At least 7 days, May 1st to July 14, 2022. It is estimated that once the cycle is completed, the well can accumulate a total of 45,000 barrels, reaching 82% of the initial estimated goal. P88 injection period. Likewise, F10 submergency fluid rate increased during P88 CSS, which indicate reservoirs are well connected. Around 4,100 barrels incremental oil was directly related to P88. P88 was under restricted production parameters due to the closure of the field between May 1st until July 14th. P88 was under restricted production parameter due to the closure of the field. F12 general comments. Artificial lift system. Jet pump has been used as an artificial lift system, the same as suggested in the initial plan. Expected cumulative production. It is estimated that once the cycle is completed, the well can accumulate a total of 34,000 barrels, reaching 90% of the initially estimated goal, which means that despite the difficulties, the well has been presenting a good performance. It is worth noting that this well were also affected by the shutdown period, and its production parameters had to be restricted for at least the frequency has been kept at 20 to 23 Hz in this period. F12 was under restriction production parameters due to the closure of the fields between May and July. F12 was under restricted production parameters due to the closure of the field. F10 general comments. The expected cumulative production. F10 is in early stage. It is estimated once the cycle completed, this well can produce a total of 37, reaching 63% of the initial estimated goal. However, it seems that the goal is overestimated, 6 times cold production and not cooling around the well for a long period. Likewise, P89 submergency fluid rate indicate F10 CSS during F10 CSS. After the F10 CSS, around 4.9 thousand barrels incremental oil was directly related to F10. Around 500. F13 general comments. The injected volume went according to plan. 15 days of injection were considered, whereas a real 13 days and a half. Soaking. After 5 hours, the pressure and temperature in tubing and casing decreased completely. Soaking plan 7 days and crawl 9 days was realized. This is the normalized performance. The learning is that longer oil length, steam tolerant, longer soaking time. F13, P89, and R56 as 57 submergency effect. This is the goal and forecast based on the current behavior, taking into consideration the previous mentioned deviation. A recalculation of the volumes to be accumulated during the cycle 1 year was made. P88, it is estimated that once the cycle is completed, this well can accumulate a total 45,496 barrels, reaching 82% of the initial estimated goal. F12, it is estimated that once the cycle is completed, this well can accumulate a total of 34,723 barrels, reaching 91% of the initial estimated goal, which means that despite all the difficulties, the well has been presenting a good performance. It is worth noting that this well was also affected by the shutdown period, and its production parameters had been restricted at least 73 days, which affected the initial peak production. If the parameters and conditions had been normal, it is estimated that final volume reached would have been much higher. F10. Although the production history is very short, an attempt was made to estimate well production forecast, and volume seems to be reduced considerably. It is estimated that once the cycle is completed, this well can accumulate a total of 37,506 barrels, reaching 63% of the initial estimated goal. Conclusion and recommendations. First, despite the difficulties presented, mostly due to circumstance of force majeure, closure due to damage of the road and the respective control of production parameters, social issues, and some contingencies with the preparation of equipment. It is estimated that the steam cycle carried out in well P88, F12, F10 allows to accumulate at least 1 million 1.1 million barrels of oil, 117,725 barrels of oil, generating in turn an increase of up to 7,000 to 4,500 barrels of oil in neighboring wells. Likewise, this incremental will leverage the fulfillment of the production goal of the term. F10 submergency fluid rate increased during P88 CSS, which indicated reservoirs are well connected between these two wells. Around 4,100 barrels incremental oil was directly related to P88 CSS from February to April 2022. This volume from F10 should be counted as the incremental of P88 CSS project. P89H submergency fluid rate increases during F10 CSS, which indicates reservoirs are well connected between P89 and F10. Around 2,450 to 4,900 barrels incremental oil was directly related to F10 CSS from July to September 2022. This volume from P89 should be counted as the incremental of F10 CSS project. P88 submergency fluid rate increases during F10 CSS, which indicate reservoirs are well connected between P88 and F10. Around 500 barrels incremental oil was directly related to F10 CSS from July to August 2022. This volume from P88 should be counted as the incremental of F10 CSS project. Parameters such as volumes of steam per feet, soaking time, and even timing between cycles are factors and detailed review and open for discussion for further CSS. An adjustment of all these factors would lead to an optimization not only of the way of producing the reservoir, but also the technical and economic resources. 3. The results to date allows us to conclude that soaking time is a crucial factor to achieve the expected result. In order to maintain the efficiency of the thermal effect in the reservoir, it is recommended that to keep the execution according to the plan. 4. It is strongly important to keep production well at high rates, since it's crucial to produce all the condensate steam water as quick as the system permits it. Delays in this process can create cooling effect in the wellbore, increasing oil viscosity, favoring the production of water by a mobility ratio and creating oil losses. 5. Jet pump generate a cooling effect in CSS cycle, so this artificial lift system is not recommended in thermal project. Changing artificial lift system in the middle of the CSS production period generates thermal shock, which decreases temperature around the valve and decrease efficiency in CSS project. Mental PCP is worldwide used in thermal projects with low failure statistics. So mental PCP is highly recommended in the CSS projects. The E&P area will continue to deepen the analysis and the learning curves of the cyclonic steam injection process in order to extend the plan to other wells and to determine what aspects of the reservoir may be influencing the results observed to date, and a detailed work plan in reservoir simulation area was proposed. 7. Considering that this project requires the participation of various areas of the company, it is recommended that each area make its corresponding analysis of the factors that were within its management in order to identify possible opportunities for improvement that can be implemented in the future and that allows to improve in their economic benefit of the project, management of communication, enlistment, and insurance of the equipment and facilities. Considering the adversity of the field, social, environmental, infrastructure, it will be evaluated to introduce an additional factor to the forecast to avoid high rate deviation.